Today we're going to talk about key features of functions. You probably remember functions from previous years in math where you talked about things like the vertical line test, increasing, decreasing, linear, nonlinear, and different features of a function. Today, we want to cover what we call key features, which is largely vocabulary and talks about what are the important things that we need to notice on a function. So these functions may be lines, they may be squiggles, but they all, if they are functions, will pass the vertical line test. So what that means is these are kind of like mathematical machines that take some input. So we have this thing called a function. It takes some inputs, they go into the function, and they come out as some outputs. Now, what the function does can vary from very simple to very complex. So we have really simple functions that we call operations, like addition. So if I put in the numbers 3 and 4 into my addition machine, out comes 7. So the number of inputs and the number of outputs that a function has varies depending on what kind of thing it is, but whatever happens, it transforms numbers into other numbers. So let's start off with a little bit of vocabulary here. Let's see, I guess we have to write it. I was going to type it because my handwriting is not the nicest, but so our fill in the blanks here, a function, which is what we're talking about, is a mathematical relationship between input and output values, where each input corresponds to exactly one output. So that's the nature of passing the vertical line test. If you remember on a graph, these x values are inputs and these y values are outputs. So -6, -5, -4, -3, -2, these are all input or x values, and the outputs are all y values. In terms of functions, we also call this x, and rather than calling this y, we call this f of x, meaning the output of that function after it acts on x. So this function has x going into it, and out of it comes f of x, which is just x transformed by that function. And that's just like a name representing what the output is, but it means the same thing as y. So on this graph, it passes our vertical line test because if I pick any input value like this one, then I go here, there's only one output value that corresponds to it. So that's the nature of being a function, and hopefully that's familiar from previous years. On a function, we have some key features that we want to look at. The first one is called x-intercepts. We also call these zeros. We also sometimes call them roots. Zeros is a really important one because it means when is the output equal to 0. Output equals 0, so we call them zeros. They're where the function returns a value or outputs 0. So our x-intercepts would be points like here, here, and here on this graph. So this particular graph has 3 x-intercepts. Now we may not be able to tell exactly what they are from this graph. We don't have enough information, but we can see that there are 3 of them. One of them is negative between 0 and -1. One is positive between 0 and 1. And the last one is positive between 2 and 3. So these are points where a graph goes through the x-axis, meaning the value of y or f of x or the output, we want to kind of think of all those as the same thing, is 0. Y-intercept, I know you're going to be familiar with, that's where the graph goes through the y-axis. And since that means the input value is 0, so the value of x or the input is 0, that means there can only be one particular output because this is a function. So while we had several x-intercepts or zeros, we can only have one y-intercept. Our y-intercept here appears to be at -1 on this graph. The domain, this is probably new terminology. So a domain we'll talk more about in the coming days is all possible input values. And and they go from negative infinity to positive infinity. So basically think of your x-axis as extending, like this arrow says, forever to the left and forever to the right, and the domain would be anywhere this graph exists within that range. The range is all possible outputs. So that's basically saying all the possible y values. So this is all the x's, this is all the y's, again, from negative infinity to infinity. But in this case, negative infinity means going down forever, and positive infinity means going up forever. So sometimes we don't want to talk about all possible values from infinity to infinity because that's maybe not practical. So a portion of the domain or range is called an interval. Typically when we look at a graph, we're focused on inputs, because if you think about our little machine, we're putting in something and then something comes out. This is less in our control. We control what goes in, because that's like the action we're taking is inputting that value. So an interval we consider to be a portion of the domain or all the x values of the graph. And we could say something like we're going to look at the interval from -4 to +2. Then we would kind of separate the graph and split it out from -4 to 2, and everything outside of that interval, so all of these values, we would just disregard those because they're not part of the interval that we're talking about. Within an interval, or within the entire domain and range, we have some new terminology that probably is hopefully reasonable, like to understand just from English words. So the first thing is the graph could be increasing. So increasing means the outputs are getting bigger. Or it could be decreasing, meaning the outputs are getting smaller. So let's take a look at this graph. I'm going to clear off the things I have on here to kind of make it easier to look at. So if we look at the interval from x equals 0 to x equals 2, in this interval, our function is increasing because the y values are going up. Whereas if we looked at it from, say, let's pick a different color, from here, where x is equal to -1 to x is equal to 0, our graph is decreasing. So this is decreasing because the y values are coming down. If we pick an interval that crosses over, like to where it's increasing and decreasing, so let's say from here to here, this interval, then we wouldn't say that it's increasing or decreasing because it goes up and then goes back down. So that really doesn't fit with increasing or decreasing. We would have to pick an interval where it's only going in one direction. So hopefully that helps you see what increasing and decreasing are. It's just thinking about following along as you read the graph from left to right, or think of it as riding a roller coaster from left to right. Are you going downhill or are you going uphill in that spot that you're talking about? The other thing we have is that the graph may be positive or negative. So positive means that the output values are above or greater than 0, and negative means the outputs are below or less than 0. Let me put that in parentheses. So let's look at our graph again. So if we looked at the interval from x equals 1 to x equals 2, the outputs are positive. So this is positive because we're above 0. We're above the x-axis. Whereas if we look at the interval from, say, here to here, like this part, then we are negative. Or if we look at the values greater, I cannot draw a straight line at all. The values here to the right, all values greater than this are negative because this arrow goes down and these are below the x-axis. So positive and negative have to do with whether the values are above or below the x-axis. Increasing or decreasing has to do with whether it's getting bigger or smaller as we head to the right on the graph. So those may be new, but hopefully they're fairly intuitive. The English words match up pretty well with the meanings on a graph. Now, we saw in one of those examples that we crossed over this hump right here where we changed from increasing to decreasing. We also have one here where we change from decreasing to increasing. These points are called a maximum or minimum, which we group together into the word extrema. It's a point where the graph changes direction. You'll do more with these in Algebra 2, and we'll do just a little bit with them when we get to quadratics in the spring. But for now, we're just going to introduce this term and move on. We're not going to get too deep into it because it's a whole big topic of continuing through high school math. But we want you to see the idea of maximum and minimum because it is a really important one for future math classes. Likewise, end behavior is something you won't deal with really till Algebra 2. And it's a way of characterizing what the graph does at the ends, or let's say what the output does. I don't know exactly what we wanted to put there, but it's what happens as you go to the end of the graph. So for example here, as we're going to the right, you can see that this arrow goes down and to the right, meaning the further right we go, the further down we go. So end behavior would be something like saying, as x approaches infinity, f of x approaches negative infinity, meaning it goes down forever, getting closer and closer to negative infinity, which infinity is a concept, not a number, so you can never reach it, but that's the idea of end behavior, is what happens as you go to the end of the graph. What does the y value do as the x value increases infinitely or decreases infinitely? But again, these two we don't really need to worry about for Algebra 1, but you will definitely be seeing them with functions in Algebra 2. We skipped over this table here. This is a way, we'll talk again more about this in domain and range, but this is a way of characterizing intervals. So when we talked about the graph above, I said things like the interval from 0 to 2. So we need a way to write that. And there's a couple of different systems. We have interval notation and inequality notation. So inequality notation, if we wanted to say all of the x values from 0 to 2, we would say something like 0 is less than or equal to x is less than or equal to 2. And then, so that's inequality. And then interval notation, we would use a square bracket 0, 2, like that. So if we wanted to say greater than 0 and less than 2, but not with equal to's, so not inclusive, we could say 0 is less than x is less than 2. And the interval notation way of writing that is with the parentheses or the round brackets instead of the square ones. So square brackets mean inclusive and round brackets mean exclusive. So this interval doesn't include 0 and 2. This interval does include 0 and 2. So again, we'll work more with this as we get into domain and range. One key thing that you can see here is that infinity always uses a round bracket because, again, infinity isn't a number, so you can never reach it. You can't include infinity in an interval. You can only approach it. So we never write less than or equal to with infinity, because this can't exist. We can't equal infinity because it's not a number that you can reach. Okay, interval notation, we're going to do a couple examples here. I just showed you one, but we're going to try to use a little bit more complex function here where it has different kind of characteristics. So we introduce here this symbol U, which means union, or if we're in delta math, you use this means or. So it means, we'll write it and then we'll read it. So decreasing, this is decreasing from here where x is 2 to here where x is 0. So we would write -2 is less than x is less than 0. The reason we do that is it's not decreasing at -2 because it increases until -2, then it basically stops for like an instant, and then it decreases after -2. So at -2, it's not going up or down. Same thing at 0, it's coming down, it stops, and then it goes up. So it's not increasing or decreasing at 0. So we would say negative 2 is less than x is less than 0 to cover this part of the graph where it's swooping down right here. But you notice there's another part where it decreases over here on the right side. And that one goes all the way to infinity, starting from x equals 1. So for that, we would write 1 is less than x is less than infinity. But to put those two together, to say that it's this one and that one, we could say or. So think of it as decreasing when x is between negative 2 and 0, or when x is between 1 and infinity. So if you're in either of those areas, it's decreasing. If we want to write that with so this is inequality notation. If you wanted to write it in interval notation, we would put negative 2 to 0, and then put this u, or union, which stands for or, and then from 1 to infinity. So interval notation is a kind of more compact way of writing this inequality notation, but we want to be familiar with both of them. The increasing intervals, on the other hand, let's switch to a different color. So we're increasing from negative infinity all the way up to negative 2. So we would put negative infinity, we're doing inequality, less than x less than negative 2. Or we're also increasing here from 0 to 1. So from 0, x, 1. And then in interval notation, we would write that as negative infinity comma negative 2 united with 0 to 1. Then for positive and negative, positive, remember, means above 0. So we're going to look at the x-axis as kind of like a cutoff. So it looks like the values are above that from when x is negative 5. We stay above this whole time until x is 4. So we're positive from negative 5 less than x less than 4. Notice again that I didn't put equal to, because at negative 5, the value, the output is 0, meaning that it's not positive or negative, so we have to put greater than, not greater than or equal to. Now, that's the only place where it's positive, so there's no second part, there's no union there. The interval version would be just negative 5, comma 4, like that. For negative is over here and over here. So from negative infinity, less than x, less than, and it ends at negative 5, that's where we reach 0. And so or 4 is less than x is less than positive infinity. And in interval notation, we would write that negative infinity, comma negative 5, united with 4 to infinity. So that's an introduction. We're going to be doing more with domain and range and using these notations, but this table in your notes is going to be a really good resource to have available. So over here on the right side, this interval notation and inequality notation is a reference that you should be looking back at over the next few days. So as we're working with domain, range, and intervals, this is going to be really helpful to look back at. I guess I didn't write this way. I wrote it the more complex way. So before we move on, let's go ahead and simplify that a little bit. So when we're writing the inequality notation, not the interval notation, we actually don't need to include infinity. We can, for this one, simplify it as just x is less than negative 5. And we can simplify this one as x is greater than 4. So we don't actually need to say less than infinity, because this says x is everything bigger than 4, which is the same as saying x is from 4 to infinity. It's the same exact thing. Okay, we have some practice here. I'm going to pick one of each kind of these to look at with you, and I'll leave the others as practice for you to do. So let's go ahead and look at number 2, and we'll look at one that has endpoints. So I guess the last one. Okay, so we'll look at numbers 2 and 6 here. And I'll leave the others as practice for you to do. Let's go back to blue. Okay, so first of all, the domain, this one has endpoints. So maybe let's just look at 1 and 2 then. Okay, so my domain for this one, I have an arrow going to the left and an arrow going to the right, meaning it goes left forever and right forever. So that means the domain is going all the way from negative infinity is less than x is less than infinity. Or if we wrote it in interval notation, that would be negative infinity to infinity. Or we call this all real numbers because it's all numbers from negative infinity to positive infinity. And we have a symbol, we can write out all real numbers. Or we can write this fancy R that kind of has like vertical, vertical, and then you connect an R like that from the top and then swoop around like that. So that's a symbol meaning all real numbers. So there's a lot of ways to write the domain here. Any of those are acceptable. The range goes down forever because these arrows point down. So we have this going down, but it doesn't go up forever. It only goes up as high as 3. So our range would be negative infinity is less than y, because with range we're talking about the y values, is less than or equal to, because this is a closed dot, 3. So we'll talk more about open and closed dots. Hopefully that's something you've seen before, but we'll refresh on that in domain and range. But a closed dot means less than or equal to or greater than or equal to, whereas an open dot means less than or greater than. To write that in interval notation, we would put negative infinity, comma, 3, and then we need a square bracket here because it includes 3. Our x-intercepts are at negative 3 and positive 3. We typically want to write these as ordered pairs, so that would be negative 3, 0, and 3, 0. Our y-intercept is at 0, 3. And you can see why just writing 3 would be confusing, because this one is 3 and this one is 3, but they're different points on our graph. So we want to include their full address as an ordered pair. We're increasing, so if we ride along this line, we're going up, 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 up until we reach x equals 0. So we're increasing from negative infinity less than x, less than or not equal to, because it's 0, it stops and turns around. Negative infinity is less than x is less than 0. And again, we can simplify that in inequality notation. We could just put x is less than 0. That means the same exact thing. So anytime I'm writing the inequalities, you could write them without the infinities. Like this could just be y is less than or equal to 3. This one you can't write without the infinities because there's no number limiting it, but you can just put all real numbers instead. Then decreasing is from 0 forever forward, so that would be from 0. Let's just write it the simpler way, which is x is greater than 0. We could put 0 less than x less than infinity, but this is easier. The graph is positive from negative 3 to positive 3, so that would be negative 3 less than x less than 3, or negative 3, 3. In interval notation. It's negative in 2 different places. So we have x is less than negative 3, that's this left part, or x is greater than 3. We can also write that as x is less than 3. Let's do it with the interval notation. So we can do negative infinity, negative 3, union 3, infinity, like that. Okay. Let's take a look at one more to wrap up. And like I said, I'll leave the others as an exercise for you to practice, and you can check with the answer keys on Canvas. This one had arrows going down. This one has endpoints all over it. So I think this would be a good one to do as a second example. Let me compare it with number 6. Number 6 is slightly more complex, but it's the same idea. So let's do number 3 here. And then I'll leave number 6 as one for you to try and then check with Canvas. So we'll do this one a little bit faster since we've already talked through all of the stuff above, and we'll just kind of breeze through it. This time I'm going to only write it in interval notation, not write it in both. So our domain doesn't have an arrow to the left or the right. It actually stops here at -5 and stops here at +4. So our domain, and it has open dots. Remember from above, open dot means less than or greater than, no equal to. So our domain will be with the round bracket or the less thans from -5 to +4. Our range, the lowest point here is -4 and the highest is +4. So if we go across the entire height of the graph, the lowest bit is -4 and the highest is +4. But these have closed dots, and a closed dot means less than or equal and greater than or equal, which we use these square brackets. Our x-intercepts are at -4, -1, and +4. But there's a trick here because this open dot means we don't actually reach that point. So this one is not an x-intercept. We actually only have 2, which are at -4, 0 and -1, 0. So the one at 4, 0, we don't quite reach it. We get infinitely close, but we never actually reach the x-axis. So we can't include that one because it's not part of our graph. Our y-intercept, we only have 1, as always, at -4. So that would be 0, -4. We're increasing from -5 to -2. And also from 0 to 4. So remember, this is 0 all the way to 4. It's going up. So 0, 4. Now we need to see how to surround that. So on the left, this is an open dot, so it's going to have a round bracket. But it ends, well, no, it ends here at a solid dot, but remember at -2, it's switching. It's not increasing or decreasing, so that'll still be a round one. These will all be round ones. Increasing and decreasing is typically, unless you're stopping in the middle of a line, like from here to here, it won't include the endpoints because when you go from an extrema to another extrema, like a high point or a low point, it's always turning around and going the other way, meaning that you're not going to include that point because it's where it switches from increasing to decreasing. And we're going to put the U in the middle here to unite those. Decreasing, there's only one interval from -2 to -4. And again, this won't include the endpoints because it's not decreasing at those points. Oh, shoot. -2 to 0. What am I doing? -2 to 0. Because we're talking about the x values, right? So this is -2 and 0. That's the portion where it's decreasing. Have I messed that up anywhere else here? I don't think so. 5, no, I think that was the first screw up I did on that, hopefully. Positive, from -4 to -1. Again, not including those because at -4 and at -1, it's 0. So positive will be -4 to -1, not inclusive. And negative will be -5 to -4. That's the left bit. From here to here, it's negative. And then it's also negative this entire way from here to here, from -1 to +4. So we're going to unite that, -1, -4. So based on what we've done here with our notes and checking with the keys on Canvas, I'd like you to try the remaining ones. So we did, I guess, the first and second of these 6, so you can try the other 4 of them as practice for filling these things in and identifying these features.